Hello everybody, my name is Ajay Sampath Kumar and today I would be talking about EUV lithography. That's the extreme ultraviolet lithography. This kind of gives you an outline on what we are going to be discussing today. First, we would have a brief introduction about photolithography, and then we would be talking about the restrictions that's there on the photolithography and why we are not able to move further. And then we would be talking about the next generation lithographic techniques. EUV lithography, that's the extreme ultraviolet lithography, is one of the lithographic techniques. We would have an introduction about it, and we're going to be discussing about the challenges that it faces, and how the technology needs to improve to support the extreme ultraviolet lithography. And then we would conclude saying, talking about the current status of EUV and the improvements that it needs to do in the future for mass production. Lithography is the process of selectively removing oxide from the substrate to implant the doping ion. Removing the oxide through uh, light sources like ultraviolet or optical sources is known as photolithography. And the lithographic resolution can be given by k times the wavelength, and the resolution improves as we decrease lambda, as most of us should have learned already. But decreasing the wavelength beyond 193 nanometers started becoming a problem, as the lens material could not support it. The photoresist started absorbing the wavelength, and mask plates didn't do well either. So we had to move towards the next generation lithographic techniques. The first one is the extreme ultraviolet lithographic technique, which is kind of the successor of the photolithography. And the next is the X-ray lithography, and beam projection lithography, and electron beam projection lithography. Numerical aperture is the maximum diffraction angle that can be delivered to a wafer. For high resolution, we want high numerical aperture and short wavelength. The lens design becomes difficult as the numerical aperture moves towards 1. The extreme ultraviolet lithography supports wavelength that's shorter than 193 nanometer, typically 157 and less than that. But the problem is there are only few refractive materials that are available, and the others get absorbed. A full refractive optical path from source to wafer is required for this. A vacuum is required from the source to wafer as well. Requires a major resist development too. To justify this huge industry change that's needed to change all these requirements, uh, the wavelength needs to be the wavelength that EUV can support needs to be uh, reduced by a factor of 10. That is from 193 nanometers to 13.5 nanometers. There are a number of challenges going forward with EUV lithography. The first of it is to develop multilayer optics coating with a reflectivity that is acceptable. The next would be to develop a new refractive mask technology which is 10 times more sensitive to defects. We would also need to have a source that could reliably and powerfully give a wavelength of 13.5 nanometers. The system needs to have a full vacuum design, and the resist technology must support good, should have good resolution and shouldn't have any power limitations and low photon numbers. The EUV technology needs to have the following advancements in multilayer reflectors, the EUV camera, uh, the source of EUV radiation, masks, and the resist. And the next sections we are going to be discussing in detail about these, and the scope of improvement in each of these. In order to achieve reasonable reflectiveness, the reflecting surface in the EUV imaging system are coated with multilayer thin films. These coating consists of a large number of alternating layers of materials having dissimilar EUV optical constants and provide a resonant reflectivity with a period of layers which is approximately the wavelength by 2. Without such reflectors, the EUV technology wouldn't have been possible. Molybdenum and silicon are the most developed alternating layers in the multilayer reflector technology. These multilayers support wavelengths up to 13 nanometers. This graph shows the molybdenum silicon reflectors reflectivity versus the wavelength, and it also shows the phase on reflection. As you can see, at 13.4 nanometers, the reflectivity goes to the peak of 0.7. The coating was designed to have a peak reflectivity at 13.4 nanometers. Designing an all-reflective camera that achieves lithographic quality imaging is more difficult than designing a refractive image system because the mirror have few degrees of freedom to vary than they do for lenses. As a result, most of the mirrors in the EUV camera will have asymmetric surfaces. The figure show, shows a schematic of the 4-mirror camera that is in the process of fabrication. The mirror segments shown in blue are the pieces actually being fabricated, uh, while the parent mirrors that shown in red are already there. The camera will be a part of engineering test standard, so it's called the ETS camera, and its features are going to be discussed in the next slide. The 4-mirror ETS camera has a numerical aperture of 0.1 and is designed to be used with molybdenum silicon multilayer at a wavelength of 13.4 nanometers. Mirror 3 is spherical and the rest of the mirrors are aspherical. Uh, this camera has a resolution better than the 100 nanometer technology. The reduction factor of the images are of factor of 4. These cameras are for the use of the step and scan lithography system. In actual operation, the mask and the wafer are simultaneously scanned in the opposite direction, with the mask moving 4 times faster than the wafer. A number of sources for the EUV radiation have been used to date in the development of the EUV. The radiation has been obtained from a variety of laser-produced plasmas and from the bending magnet. Our work has used a succession of continuously improved laser-produced plasma source. Work is being done on the development of discharge sources that might be able to provide adequate power in the desired wavelength. Eventually, a source will be required that has sufficient power uh, to yield adequate wafer throughput in the manufacturing tool. The EUV masks are reflective and not transmittive. They consist of patterned absorber of UV radiation placed on the top of the multilayer reflector, deposited on a robust and a solid substrate such as a silicon wafer. The membrane masks are not required. It is anticipated that the EUV masks will be fabricated using processing technologies that are standard in the semiconductor production. Nonetheless, there are a number of serious concerns about mask development. The foremost is the fact that there is no known method for repairing defects in a multilayer coating. Since the masks must be free of defects, a technique must be developed for depositing defect-free multilayer reflectors. As we had discussed before, it's difficult to find resists that can work below 200 nanometers of the source wavelength. That's because it starts absorbing the wavelength, the light. But there are some active resists that have been developed, like the single layer resist, the bilayer, and the trilayer. So these are the resists that are being tried to use in the EUV technology. A successful resist must also possess excellent etch resistance. To conclude, let's talk about the status of EUV. This is a foil that I pulled out from Intel, and this talks about the various technology that we get discussed before and the status of how they are doing. If you look at the resolution is on track, but the dose needs high power. If you look at the tools, uh, the source availability seems to be critical and power is also critical, so that's not doing well. But the scanner hardware is on right on track. So the work is still in progress for mass production of wafers using EUV. These are the references that I had used uh, to give this presentation. You could go through them, they are really informative. Thank you for listening to my presentation on EUV lithography.